at MIT, Cobley Fellows. So she's been there for like about a year and continuing her work there on streams and intersections with cosmological simulations. And as you'll tell, she's one of the leaders, if not the leader, in this sort of burgeoning topic that's really developed in the past few years. So she's going to talk to us about too big to fail stellar streams in simulations in the Milky Way. So thanks.
Great. Thank you so much for the introduction and for the opportunity to share some of my work with you. So I will be talking about stellar streams as probes of near-field cosmology. First, I'll give a bit of an overview of the population of streams that we've observed in the Milky Way and some of the work that we've done over the past several years on building up the first population of stellar streams with systematically observed 60 position and kinematic measurements. And then I'll talk about how we can compare these streams to analogous stream populations in cosmological simulations to learn about both dark matter and galaxy formation in the local universe. So in particular, I will both ask and answer the question, is there a too big to fail problem in stellar streams?
We know the answer.
You may know the answer. My gift is not working. Okay. Well, so stellar streams, for anyone who isn't already familiar, are the tidal remnants of globular clusters and dwarf galaxies that are disrupted as they orbit around a host system like the Milky Way. This is supposed to be a simulation, but here's just a still of it showing the disruption of some of these systems. So essentially they get tidally disrupted and torn apart until they form these long streams of stars that extend across the sky. And stellar streams are really sort of an in-between point between the intact satellites that are first accreted onto the Milky Way and systems that have been fully phase mixed and blended into the broader Milky Way system. So they retain this coherent structure in phase space, which makes them easier to discover, easier to observe, and easier to model, and also makes them excellent probes of both dark matter and the evolution of our galaxy. So there are a lot of reasons why we're really excited about studying stellar streams. So one is that they're excellent probes of the local gravitational potential. So because they're very extended, they probe a large volume of the Milky Way's potential, and their formation is very sensitive to the tidal forces in the gravitational field in which they're disrupting. So this means that we can model the orbits and the formation of these streams in order to measure the total mass of the Milky Way, as well as the mass of structures orbiting our galaxy, and also to measure the shape of the Milky Way's dark matter halo. On smaller scales, stellar streams are also very sensitive to the local distribution of dark matter. So they're actually one of only a couple proposed methods for detecting completely dark subhalos. So these are subhalos with no luminous baryonic component. We can't detect them using our usual methods. But because stellar streams are orbiting out in the Milky Way's halo, along with this predicted population of dark subhalos, we expect that sometimes they should interact gravitationally and they can leave behind distinctive density features. This is a figure from a paper led by Anna Benazza showing the GD1 stellar stream, which has some interesting density variations. You can see here, there's some lower density regions, which could perhaps be caused by an interaction like this. So by studying the density of stars along stellar streams, we can indirectly infer the population of low mass dark matter subhalos, which are very sensitive to properties of dark matter. Here's just a prediction that we made for the detection of these low mass subhalos with LSST. So this is looking at a single gap caused in a stellar stream by an interaction with a single dark matter subhalo. So the green line is showing the prediction for 10 years of LSST data. So the y-axis is the mass of that subhalo that's interacting with the stream, and the x-axis is the surface brightness of the stream. So it depends on how bright the stream is, but we expect that we should be able to get down to quite low masses, maybe even between 10 to the 5th, 10 to the 6th solar masses, which will enable very strong constraints on things like warm dark matter particle mass or dark matter self-interaction cross-section. And streams, of course, are also excellent probes of the stellar component of our galaxy. They provide a sort of snapshot of the accretion history of the Milky Way and the disruption of Milky Way satellites. So by studying streams, we can reassemble the buildup of the Milky Way's stellar halo. We can also learn about the physics of tidal disruption and how the population of satellites around the Milky Way evolves over time. So here are three of the primary goals in the study of stellar streams. So first, we need to discover these systems, and we need to precisely measure their positions and velocities. Second, we can model these systems to measure their orbits, to learn about the formation of these individual systems. And this can also tell us about the local gravitational potential. And then finally, we can study these systems as a population and make comparisons to theoretical predictions, often from cosmological simulations, in order to constrain models of galaxy formation and dark matter. So I'm going to touch on each of these areas and talk about some of the work that I've done. So first, I want to talk about the discovery and the observation of a large population of Milky Way stellar streams. Okay. So in order to do any of the science that I've described, we really need a large population of stellar streams, and we need complete 6D position and kinematic measurements. So for example, if we want to model the orbits of streams in order to measure the Milky Way's gravitational potential, it's essential that we have all of this velocity information. And until recently, this was very difficult, but with recent large astronomical surveys, we've been able to build up this first population of Milky Way streams with complete 6D phase-space measurements. So there are several different groups working on observations of streams, but for the purposes of this talk, I'll focus on some of the work that my collaborators and I have done for the past several years, and primarily during my PhD, on building up a population of streams observed in the southern sky. First, I led the search for stellar streams in the dark energy survey. So I'm sure many of you are very familiar with DES, but it's a wide area survey. It's very deep, has very precise photometry, it's very uniform. And so for all of these reasons, it's really excellent for looking for these very faint stellar density features. We search for streams in DES by filtering the data in color magnitude space. So that's what I'm showing in this animation on the left here. It's showing just for a single globular cluster. This is a spatial plot. And then on the left is the same data in color magnitude space. So we build this filter to select old metal poor stars that are typical of the stellar populations that make up the globular clusters and dwarf galaxies that disrupt to form stellar streams. And then we shift it in apparent magnitude, which is shifting in distance, to probe these structures at a range of distances out into the Milky Way stellar halo. So in that animation, you can see that as the filter lines up with the data on the left, the cluster in the middle panel really comes into focus and then sort of fades away. And that's exactly what we're doing in this animation on the right, but with data across the entire DES footprint. So here, darker is higher density. These are stars that have been filtered to select out these likely stream member stars, more likely stream member stars, and we're looping through distance, which is labeled at the top left. So you can see all of these dark linear features that are the DES stellar streams. There's really a large number of them that are sort of crisscrossing and orbiting out at a range of distances into the Milky Way halo. So within DES, we discovered 11 new stellar streams and improved observations of 4 previously known streams, which more than doubled the number of known streams at the time in the southern hemisphere and increased the total population of streams by about 50%. And in addition, here are all the streams, their positions and their names marked. In addition, just because of the quality of the DES data, these are some of the faintest, lowest surface brightness, most distant streams that we've observed in our galaxy. So this is a really population of stellar streams for studying the Milky Way halo, as well as a population of disrupting satellites in our galaxy. We were lucky that soon after we published the discovery of these DES stellar streams, Gaia DR2 came out. So Gaia has really revolutionized the study of stars in our galaxy by providing very precise position and proper motion measurements for more than 1 billion stars. So one point about Gaia is that it's not as deep as DES. So we weren't sure at first whether we would be able to get proper motion measurements from Gaia for all the streams that we were able to see in the DES data. But by taking advantage of the very precise DES photometry, as well as these proper motions from Gaia and cross-matching these 2 data sets, we're able to measure proper motions for even the most distant DES stream, which is at 50 kiloparsecs. One important science result that came from this, which I'm showing on the left here, is that we found that most of these streams have evidence of significant perturbation. So here, this again is the DES footprint. The black lines are the stream tracks on the sky, and the blue arrows are the proper motions. So for streams on unperturbed orbits, you would expect their direction of motion to line up with the track of the stream on the sky, but you can see that most of these blue arrows are pretty significantly offset. So it's a sign that these systems have been somehow perturbed from their original orbits. And I'll come back to this in just a minute. But first I want to talk about S5, or the Southern Stellar Stream Spectroscopic Survey. So with DES and with Gaia, we have all the position coordinates, and we have those 2 velocity coordinates on the sky, but we still need radial velocity measurements. So for that, we need a spectroscopic survey. And And so S5 is a survey that's led by Tim Lee, an A&M alum. And many people here are familiar with S5 and members of S5. But S5 is a spectroscopic survey of stellar streams across the southern sky with the goal of measuring radial velocities and metallicities of all of these systems. And prior to S5, there was no systematic spectroscopic survey of stellar streams, and this was largely due to the difficulty of target selection. So streams, because they are disrupted galaxies or globular clusters, have their mass extended over a large area in the sky. So they're very diffuse and they take a lot of time to observe, especially if you can't efficiently select likely member stars. But by taking advantage of the precise photometric measurements that we got from DES, as well as the proper motions that we got from Gaia, we were able to significantly increase the efficiency of target selection. And so far, S5 has been able to observe more than 20 stellar streams in the southern sky. So here's a figure from a recent S5 paper that was led by Ting, which shows the first dozen streams observed by S5. So we're now at more than 20, but these are the ones that were included in our first data release. So you can see that we followed up most of the streams in the DES footprint, as well as several others across the southern sky. This is really important. It's the first time that we've had a population of streams like this with all of these detailed 6D measurements. We also have metallicity measurements. This is essential for being able to model the orbits of these systems, also for being able to determine which ones come from globular clusters versus dwarf galaxies, and inferring properties like the original masses of their progenitors. So I won't go into detail on all of the exciting work that's come from S5, but I just want to quickly flash some of our papers, and I definitely encourage you all to take a look. We have papers on extremely metal poor globular cluster streams. We have a hypervelocity star. We have measurements of the local gravitational potential. So there's a lot of exciting work coming from S5. So now we have this really excellent population of Milky Way streams. So we can model these systems to measure their orbits and to measure the local gravitational potential. So here I want to focus on one particular science case, which is measuring the mass of the Large Magellanic Cloud. The LMC, of course, is the most massive satellite of the Milky Way. It has a mass of at least about 15% that of the galaxy, which means that it's a very significant perturber to the Milky Way system. So the LMC has a strong effect on the total satellite population of the Milky Way. It has a strong dynamical effect on any structures that are orbiting within the Milky Way halo. And it can even cause bursts of star formation in the Milky Way. So if we want to understand our own galaxy or understand systems that are orbiting within the Milky Way's halo, like stellar streams, it's essential that we also have a very precise understanding of the effect of the LMC. So fortunately, streams are extremely sensitive to the LMC and can give us measurements of its total mass. So most previous mass measurements were within a relatively small radius, but with streams, we can get measurements of the total dynamical mass of the LMC. So I'll play this movie again. So here's an example of the Orphan Chenab stream. So the black is the data here, and the blue is a model of the stream disrupting. Then you'll see the LMC come in and really pull the southern part of this stream off of its original orbit, shown by that black dashed line. So it lines up nicely with the data. And this is something that we can't reproduce without including the effect of the LMC. So we really see that these streams have been significantly affected. And then back to this figure that I showed earlier with the proper motion measurements from Gaia. So I mentioned that we found that these streams had evidence of significant perturbation. Well, it turns out that it's actually due to the Large Magellanic Cloud. So the LMC is located right here, just off the edge of the DES footprint. And the orange line shows its past 1 gigayear orbit. So you can see it's really passing through this DES stream population. So here's another movie showing more of the DES streams all orbiting and disrupting together. Then again, the LMC will come in here and it'll simultaneously perturb all of these systems. The orange here is the Orphan Chenab stream again, so you can see that significant offset. Others also have smaller offsets that you might be able to pick out. But essentially, we can build up this consistent picture of how this population of stellar streams has been perturbed by this one single massive perturber in our galaxy. And because these streams are so affected, we've also been able to use them to actually measure the total mass of the LMC. So here it's showing the posterior distribution on the LMC mass from 5 of those 60 stellar streams. So you can see they're quite consistent. We're really building up this nice picture of how all these systems that are orbiting differently, have different approach times and approach distances around the LMC are affected by this single system. And we get a measurement of the LMC mass that's closer to 20% of that of the Milky Way. This is the first time we've been able to get a measurement like this using a population of stellar streams to measure something like the mass of the Large Magellanic Cloud. And within S5, we're continuing to build upon this work with the ultimate goal of simultaneously modeling an even larger population of stellar streams to measure the joint potential of the Milky Way and the LMC.
Okay.
Yes.
Does this require any special knowledge of the LMC's orbit? Like, does this require knowing that LMC is on its first infall or like anything?
No, so we could add that in as an additional constraint, but what we do is we have measurements of the proper motion, the radial velocity, distance, et cetera, the LMC, and then we allow those to vary within measurement uncertainties in the LMC grading as well. So that's how we've treated it.
What do you mean by the mass of the LMC? Is it like the infall mass or is it the current mass?
Yeah, so that is what I'm going to get to next,
Okay.
basically, which is that the mass of the LMC is changing because it is disrupting as it falls into the Milky Way. So here, what we're measuring is the infall mass.
The mass it had before it fell in.
Roughly. I mean, so in this model, the LMC's mass is not changing. It has a fixed potential, and it also just, it's not deforming. So it's a fixed spherical potential. But we're now within S5 building upon this to include a more complex model of the LMC potential. So Sophia.
Sorry, can I, Justin, if it's too long of a question, you can go back to it at the end. Like, I think there's no assumptions about the LMC's orbit in this at all. And in this to get this figure, right?
Well, we have measurements of the current.
So you have the measurement of the position, but then you use that
LMC. And then we integrate it back
okay,
in the Milky Way potential we're using.
So in some sense, okay, okay. So, I guess there's a model for its orbit based upon
there is a model.
Okay.
Yes.
Can I ask you a question from the person online?
Go ahead.
Sure. So for the LMC, I mean, I missed this if you said it. Is it just really you're assuming it's one spherical potential, so it's the whole Magellanic group, or does the effect of the SMC and the other little satellites contribute to the perturbation here?
Yeah, so this is not including the SMC right now. This is just the LMC. But I did do some tests to sort of not fit the mass of the SMC, but throw it in and see how it perturbs these systems on top of the perturbation from the LMC, and the effect is much smaller. So, eventually we would like to include that as well, but it doesn't have a significant effect on this result.
Okay, so the takeaway is the LMC is really the main perturber for this situation, or for based off what you're seeing in the streams.
Yes.
Okay, cool.
I guess while we're on the topic of history, are you assuming that the streams are in like a multiple passage scenario where they've kind of like, at least looking at that earlier video that you showed with all the different streams, it looked like they had already sort of like settled into like nice orbits, even though the streams are still stretching out. It's like, I would imagine like if they're falling in, I'm just thinking from like a galaxy tidal tail perspective, where the tail kind of like gets swept outwards, and so the motion isn't all along the stream direction, it's like tangential or perpendicular to that rather.
Yeah, so the way that I model the streams here is using a particle spray method. So it's not full n-body simulations or anything. Particle spray means that we integrate the progenitor along its orbit, and then you spit out particles at sort of regular time intervals from the Lagrange points. So it doesn't sort of include the full evolution of the stream from like fully intact to stream in a fully realistic way, because it just has this like fixed disruption rate kind of. But it does reproduce realistic stream models and doesn't require that they're following in orbit exactly. So this, because each particle is then integrated in the progenitor and the Milky Way LMC potential, there's room for sort of like these perturbations along different parts of the stream, if that makes sense.
Yeah.
Yeah. Okay. So the next step is to consider the fact that the LMC is deforming, and the Milky Way is actually also deforming in response to the LMC. So Sophia Lillingen, who is a PhD student at the University of Surrey and actually on the job market this year, has been exploring the effect of the deforming Milky Way and LMC on the orphan Chenab stream. So that's the one that I showed in two of those movies before that's most significantly affected by the LMC. So here is a figure from her paper showing the density of the Milky Way, the LMC, and then the joint potential here. You can see that LMC is very deformed, and the Milky Way, especially these inner parts here, also deforming in response to the LMC. So this is from an n-body simulation. And so what she's done is fit basis function expansions to this potential here, and then run the stream models in this potential on the simulation to see how the different deformations affect this one stream. So this figure is showing what happens when you include different parts of this potential model. So on the left, she has a fully live Milky Way. So it's the full potential from that n-body simulation, and then different components of the LMC potential. And on the right is fully live LMC and different components of the Milky Way. And then the x-axis here is the position along the stream, and the y-axis is the sort of perpendicular position relative to the stream track. And it's the residual relative to the stream in the fully live model. So sorry, it's a little bit complicated, but the important point here is that these models here are the ones that have the largest residual, and these are the ones that are excluding the dipole component of the Milky Way potential. So she found that it's actually not the deformation of the LMC, but the deformation or the stretching of the Milky Way in response to the LMC falling in that has the most significant effect on these streams. So it shows that this is really essential to include when we want to get a full understanding of how these streams are affected by the local gravitational potential and ultimately measure the storing potential of the Milky Way and LMC. This is just to show that these streams actually include different and complementary information about the LMC potential and the Milky Way potential. But this is showing the position around the LMC of each stream at closest approach. So it's essentially longitude and latitude around the LMC. And then the points, the size is inversely proportional to the distance of closest approach. So TUC3 here has the closest approach to the LMC, and then some like Indus and Jalen here are further away. But essentially these streams at different times are passing close to different parts of the LMC and at different distances. And then you can see LP here is our most distant stream, and this one's actually passing on the other side of the LMC. So even with the streams, and as we continue to add in more streams and discover more distant streams that might be more on the LP side, we're really getting information from each of these systems that's very complementary, and we can use to build up this complete picture of the asymmetrical, radial, time-dependent profile of the LMC.
Is there a disk in these simulations? The Milky Way disk?
Yes. Yeah. Okay. So for the last part of this talk, I want to talk about these population level studies of stellar streams. So this is something that I'm really excited about right now, and that we've only been able to do for the first time now that we have this population of very well observed stellar streams in the Milky Way. And we also have cosmological simulations that are now at high enough resolutions that we can identify dwarf galaxy streams around Milky Way mass galaxies. So I'm actually working with a few different simulation groups now, but for this talk, I'm going to focus on the fire simulations. So these are fully cosmological hydrodynamic simulations within fire. The suites that I'm primarily interested in are the Latte and Elvis on Fire suites of simulations. So Latte is zoom-ins of Milky Way analogs, these are isolated Milky Ways. Then Elvis on Fire is zoom-ins of local group pairs, so Milky Way Andromeda pairs. And this movie here is showing one of the Latte galaxies. So you can see it creating this nice population of satellites and disrupting them, and you might be able to pick out some of these stellar streams that are forming here. Okay, so of course, these sorts of comparisons between simulations and observations of satellite populations have been done with intact satellites for many years now. And these studies have taught us a lot about galaxy formation at the smallest scales and have raised challenges to the standard cold dark matter model, like the missing satellites problem, the Corcus problem, too big to fail problem. Many of these have now been resolved by incorporating more complex baryonic physics into our simulations. So now these state-of-the-art cosmological simulations, including fire, do a really good job of reproducing properties of intact satellites, which is what I'm showing here. So here on the left is the stellar mass function of intact satellites, so we're not including any streams here. So the black solid line is the Milky Way, and then all the colored lines are different simulated fire galaxies. You can see they line up pretty nicely. The dashed line is Andromeda, which is actually a higher mass than any of the simulated fire galaxies, so that's probably why it's offset a bit. And then here on the right is the radial profile of satellites Again, the solid black is the Milky Way, and then this blue shaded region kind of shows the scatter between all of these fire simulations. But essentially, we're seeing that we're doing a pretty good job of matching these properties of the surviving satellite population. But now by including stellar streams, which we're only able to do now for the first time, we can even further challenge our simulations to reproduce the full population of satellites that we see in the Milky Way along the full spectrum of disruption from fully intact to phase mixed. And this is important because, one, it increases our sample size of satellites that we're considering, but also because stellar streams provide a test of the disruption rate of satellites, which is a huge uncertainty in studies of near-field cosmology and extremely sensitive to the inner structure of these low-mass galaxies, which in turn is very sensitive to both galaxy formation and dark matter properties. So this really gives us new, very strong tests of both dark matter and small-scale galaxy formation by incorporating stellar streams. So last year, non-dependent Taisan, who's a PhD student at UPenn and also on the job market this year, he identified stellar streams around the 13 Milky Way analogs in fire. So these are the Latte and the Elvis on fire simulations. This grid here, I'm just showing a selection of some of these simulated fire streams. So these streams have stellar masses down to about 5 × 10⁵ solar masses, just due to the resolution limits of the simulations. And this is not covering the full range of streams that we've observed in the Milky Way, but it does give us some nice overlap in parameter space where we can begin to make these comparisons. I won't go into detail on how we select the streams, but just to show some examples of here's what's considered an intact satellite, a phase mix system, and a stream in fire. And essentially the selection is based on the number of particles so that we ensure that we only select systems that are fully resolved, on the max pairwise separation, which means that these are extended structures, not intact satellites, and then on the local velocity dispersion, which just selects between systems that are fully phase mixed and that still have this coherent stream structure. And we do confirm all of this by eye that we're doing a good job of selecting the structures that would look like streams if we observe them in the Milky Way. So now to the question, is there a too big to fail problem in stellar streams? So the first very quick comparison that you can make once you have this population of Milky Way streams and population of simulated streams is to just count them up within the same stellar mass range and see how they compare. So this is what you get. So here, each bar is one of the 13 simulated fire Milky Ways, and they're actually ordered in order of increasing host halo mass. So Romulus is most massive and 12R is least massive. And here I'm showing the number of streams. Then in the background, this gray bar is the number of streams in the Milky Way in this stellar mass range. So it's 2 to 3-ish. And here you can see there's this clear discrepancy. The fire simulations seem to have a much higher number of very high stellar mass streams than we see in the Milky Way. So this is what we've referred to as a too big to fail problem, where here just means, is there an excess of very bright or very high stellar mass streams in simulations compared to the Milky Way? Another way to look at this is to look at the stellar mass function of streams. So here, again, the gray is the Milky Way, and these stellar masses come from S5 metallicity measurements, which give us estimates of the total stellar mass of these systems. So it doesn't require that we've observed the full extent of each of these streams, but an important point that I will get to is that it does not take into account now whether we've discovered all of the streams in the Milky Way. And don't worry, I will address that.
So actually, you kind of answered the mass question. It's the mass measurements, the mass deductions of this observed stream comes from the metallicities.
Comes from the metallicities.
You go to mass metallicity relation.
Yes.
Okay. Yeah. Because observing the mass of the stream is probably very difficult.
Yeah. Right.
From the handful of stars.
Yeah. And then the blue here are the simulated streams. So light blue is Latte. Those are the isolated Milky Ways. And then dark blue is the Elvis on fire simulations. So these are the Milky Way Andromeda pairs. And they're plotted separately just because they have slightly different resolutions. So the paired ones are slightly higher resolution, and to examine whether there's any difference between isolated versus paired Milky Way systems.
That's a follow-up question about what you just said. So couldn't you, these are simulations, so couldn't you just run them backwards and then measure what the mass of the progenitor was when you see the progenitor?
So for the simulations, we do that. Yeah. It's for the observed streams that we're getting the masses from the metallicity measurements.
Oh, sorry, I misunderstood.
Yeah, sorry.
But did you do it that way?
Actually, yeah, that's our
good. So the Fire 2 simulations that I'm using here actually don't have super reliable metallicities. Yeah, so there are also the Fire 3 simulations, which have some updated physics and have slightly better metallicities. So that's something we could look at in the future. Yeah, but here it was just a little bit safer to use the stellar masses from the simulations directly and then to get stellar mass measurements from the observed metallicities.
Sorry, like one more quick question. Can you remind me the difference between like how Latte and Elvis treats the baryons? Because one does like abundance matching and one doesn't. Is that or the
no, so these are resimulations of the dark matter only Elvis simulations. So it's the same Fire 2 physics as the Latte simulation.
There's no abundance matching for like in
no, there's no
just,
yeah. So Latte, the ones that I'm showing here, the Latte and Elvis on Fire, okay. The on Fire specifically, are treated exactly the same, simulated in the same way. Okay. Yeah, the resolution is just slightly different. Any other questions before I move on? So we can also look at this by combining the streams with intact satellites. So here on the left is the same figure that I just showed. This is just the streams. And here on the right is streams plus intact satellites. So you can see it's a little bit more consistent. And one of the important points that we're seeing in Fire is that actually many of the surviving satellites have extended tidal tails and would be classified as streams if we could detect those tails. So this is almost 50% of the surviving satellites we have classified as stellar streams, which does suggest that it's important when we're doing these comparisons, even of intact satellites in Fire and the Milky Way, that we include things like Sagittarius that have a surviving progenitor, even though they are technically stellar streams. And then here in the middle, I'm showing intact satellites only. So these are in Fire, only the things that have no tidal tails at all. Okay, but of course I mentioned the point that we have not yet detected every single stellar stream in the Milky Way. So when you're looking at these really high stellar masses, really high luminosities, it's a little bit more uncertain how complete our stream population is. But in order to address this, produced mock dark energy surveys of the Fire streams and estimated their detectability. So this enabled us to accurately compare analogous populations. So it's only detectable dwarf galaxy streams in this mass range in Fire compared to streams in this mass range in the Milky Way that we have been able to detect. We produce these mock observations using Ananke. So this is a code that was developed by Robin Sanderson, originally used to create a mock Gaia catalog of the Fire simulations. So here is a figure from Robin showing on the bottom real Milky Way data, and on the top, the mock observations of one of these Latte galaxies. And while I'm mentioning it, I'll also plug that we're currently working on creating a mock Gaia DR3 catalog using Ananke, which should be out very soon. But for this work, I adapted Ananke to work with the DES photometric system so we can create mock dark energy survey observations of the Fire stellar streams. So I picked DES because it's the best data set that we have right now for discovering these very faint and distant stellar streams. And essentially, we can say that if we assume there's DES data across the whole sky, and the detectability estimate tells us that there is no too big to fail problem in stellar streams, then using a more complete estimate of detectability in different surveys will do even more to resolve this problem. So once we create these mock dark energy survey observations of the stellar streams, we estimate their detectability, and we do this using a methodology that's motivated by the stream search that I conducted in DES. So essentially the detectability is based on the surface brightness of these streams. So this is the surface brightness of the resolved member stars. So this is something that we calculated for the DES streams, and here we calculated it in exactly the same way for these mock observed simulated streams. We calculate the surface brightness along each of these streams in 15-degree long bins to account for the fact that there is variation in the density along these streams. So some parts might be observable while some other parts are not. So here is just a couple examples. So here blue is detectable and green is undetectable. So here's one where pretty much the whole stream is detectable. We have some that are fully undetectable, and then we have some that are kind of mixed where they have some really bright components and then maybe a more diffuse lower surface brightness component that's not detectable. And we also consider the progenitors of these systems separately. So some of these streams have surviving progenitors, some of them do not. For the ones that do, we mask out the progenitor when estimating the detectability of the tidal tails. And then we use a separate detectability estimate from Wagner et al. 2020, which is the Milky Way satellite census paper, to estimate the detectability of those progenitors as well as the intact satellites in fire. So we find that among the progenitors and intact satellites, most of them in the stellar mass range are detectable, but a very big number of the streams would not be detectable. So here's an updated version of this figure that I showed earlier, taking into account the detectability. So here, the dark blue at the bottom is what you should be comparing to the Milky Way line in the background. So these are the number of detectable streams in each of these simulations. And you can see this is much more consistent now. So I would say there is no too big to fail problem in stellar streams. But what's interesting is that the fire simulations are predicting that our population of even very high stellar mass streams in the Milky Way is actually quite incomplete. So the total height of the bar is the total number of streams. This lightest component here is the number of undetectable streams. So we don't detect any component of them or their progenitor. And then interestingly, this middle blue bar here are the number of streams that have a detectable progenitor, but undetectable tidal tails. So these are systems that would be mistaken as intact satellite galaxies if we observe them in DES in the Milky Way. So this is suggesting that perhaps many of the systems that we think of as intact satellites could have these very low surface brightness, yet undetected tidal tails. Okay, so now we can come back to this figure looking at the stellar mass function of streams plus intact satellites and intact satellites only. This is the same one that I showed before with the total number of systems, but if instead we only look at the detectable systems, it looks like this. So you can see that all of them are much more consistent. The streams match up quite well in the streams plus intact satellites. For intact satellites, here I just want to point out that this is both excluding any intact satellites that are not detectable, but also including any of those systems that would be mistaken as intact satellites. So it's only when we include these systems that are truly streams, but that would be observed as intact satellites, that we can reproduce the stellar mass function that we see in Milky Way intact satellites. So we can use this to make predictions for detectability in future surveys like LSST. So LSST will be excellent for discovering more stellar streams. It's very similar to DES, but covers more of the sky to fainter magnitudes and with even higher precision photometry. So here I've used Ananke again to create mock Rubin observations of all of the fire streams and plotting the number of detectable streams as a function of the surface brightness limit. So for DES, the surface brightness limit is 34, and we determined that just by actually calculating the surface brightness of the streams that we detected in DES. It's very difficult to predict exactly what this limit will be in LSST without having our hands on real data. But essentially, we can say that once we start discovering new streams, if we're seeing streams with surface brightnesses of 36 or even fainter, then we really expect to see about 5 to 6 of these high stellar mass streams in the Milky Way. And this will enable us to continue to test whether our simulations are truly consistent in terms of the number and the stellar mass functions of streams. To make predictions for which of the intact satellites in the Milky Way may be more likely to have tidal tails based on what we're seeing in fire. So here I'm plotting as a function of distance from the host galaxy, the fraction of satellites that have detectable or undetectable tidal tails. So blue is detectable and light blue is undetectable. So these are detectable progenitors, undetectable tails. And then the error bars just show the scatter between simulations. You can see that in some of these bins, there's a huge amount of scatter. But this does suggest that perhaps in this range from about 50 to 200 kiloparsecs, a very large fraction of satellites should have yet undetectable tidal tails. Right now, the ones that we know about are Sagittarius and Antlia 2 that are within the stellar mass range, and those would be in these distance bins.
So 100 kbc, mine's so low detectable there, but then suddenly it jumps again.
That is a good question, and I don't think I have a good answer right now, but it would be interesting to look into that more.
Noise.
Yeah, it might be. Okay, so We are doing a great job in FIRE of reproducing the number and the stellar masses of stellar streams, but there is a really important discrepancy that I do want to highlight that shows that FIRE is not exactly reproducing the stream population that we observe in the Milky Way. So that's in the orbits of these systems. So here I'm showing the pericenters and apicenters of Milky Way streams, the black X's down here, and FIRE streams, which are the bluish, purplish circles and triangles. So on the right is the total population, regardless of detectability, among the 13 Milky Way analogs. And on the left is only the detectable population. So you can see that even when we take into account detectability, there's a very clear difference in these orbital distributions. So the FIRE streams are disrupting at much larger pericenters, even out to 100 kiloparsecs, and only exist at larger apicenters. So this is really interesting here that there's no FIRE streams within about 50 kiloparsecs because maybe we need to add more complexity to our detectability estimates, et cetera, and perhaps that could explain some of these really distant systems, but it would not explain the fact that there's no FIRE streams with apicenters of less than 50 kiloparsecs. So there's a very clear discrepancy here, and this tells us that there's still something important that we're missing in the way that we're modeling baryonic and dark matter physics in these state-of-the-art cosmological simulations. And then I'll just mention the color bar here is a look back time at accretion. So darker purple means they were accreted earlier. So you can see the differences between the detectable and the total population suggests that the streams that are yet to be detected are mostly systems that are at larger distances or systems that are were accreted earlier and are lower surface brightness, more phase mixed. So those are the ones that we would expect to see in the Milky Way with future observations if FIRE is indeed correct. Okay, so here's just another look at the pericenters and apicenters of these systems and looking at systems at different stages of disruption in FIRE. So again, the black is the Milky Way dwarf galaxy streams. Blue is the FIRE stream, so that's the same as the points that I showed on the previous plot. Purple is surviving satellites in FIRE, and green is phase mix systems. So interestingly, we're seeing that the phase mix systems in FIRE have pericenters and apicenters, more similar to stellar streams, not phase mixed in the Milky Way. So that could tell us that FIRE is somehow over disrupting streams, disrupting them too quickly on the wrong orbits. There's something going on that's leading to this difference in the orbital distributions of streams in FIRE and the Milky Way. And I'll also mention that there definitely is uncertainty in the orbits of the Milky Way streams and how we've modeled them, but I did do a lot of tests to explore the effect of assuming a time independent versus dependent potential. We've also included the effect of the LMC, and none of it is sufficient to explain this discrepancy that we're seeing here. So one more point is we can look at the systems that are disrupting in FIRE and their orbits and their densities and predict whether it makes sense that they are disrupting. So this is motivated by a figure created by Andrew Pace looking at real dwarf galaxies observed in the Milky Way. On the x-axis is the pericenter of these systems. On the y-axis is the density within the half-light radius. And then this line shows the average density of the Milky Way within this distance. So systems on this side here have a tidal radius that's smaller than their half-light radius, which means that we expect them to be disrupting, whereas systems that are on this side of the line have a tidal radius that is larger than their half-light radius, and we don't expect them to be disrupting as much. So we can do exactly the same thing with the stream progenitors, as well as the intact satellites in FIRE. And this is, again, from the mock DES observations using exactly the same code that's used for DES dwarf galaxies or Milky Way dwarf galaxies to measure these structural parameters like the half-light radius. And so here, these points are color-coded by the fraction of stellar mass that's been stripped and is in the tidal tails. So the ones down here that are more yellow, more green are more stripped than the purpley ones up here. So you can at least see that this trend makes sense for the systems that are further down in this direction are more disrupted, but there is a large number of systems that are classified as tidal streams and have some fraction of their mass in tidal tails that are significantly above this line. And so one of the interesting things, sorry, this is a more complicated point, but one of the interesting things that we're seeing is that it's actually not that a huge fraction of the mass has been stripped into these tidal tails, especially for these systems with very large pericenters, but that they have these more extended stellar distributions, and those are the stars that make up these tidal tails. So they become very extended, but it's a small fraction of the stellar mass, mostly around 10%, that is stripped into these extended low surface brightness tails. Okay. So there are several possible explanations and a lot of, I think, very interesting next steps that we can take to explore these differences that we're seeing between the stream population and simulations and observations. So one, a big question is it just due to the resolution of the simulations? So resolution issues can lead to artificial numerical disruption. There have been a lot of tests in FIRE that suggest that in the stellar mass range that we're looking at, this does not affect the population of FIRE satellites, but I am currently planning to look at the triple latte simulation. So this is the same as the latte simulations, but 8 times higher resolution. So we have the same galaxies resimulated at higher resolution. So by studying the same stream populations there, we can see whether resolution is truly affecting the disruption rates of these systems. There's also a question of whether it's sort of the specific feedback models of FIRE that could be leading to over disruption. So FIRE has a very bursty stellar feedback model that could sort of blow out material and lead to larger sizes and a sort of puffiness among their satellite galaxies, which could potentially lead them to be disrupting faster than the satellite galaxies in the Milky Way. In order to address this, I'm also looking at other simulation suites, so especially the Auriga suite of simulations, also Winter-Gatan and possibly Illustris, to look at stream populations and simulations with totally different feedback models. So right now, this is pretty preliminary, but I am seeing the same difference in the orbits between simulated and observed streams in Auriga. So it looks like it is not due solely to the feedback physics in FIRE. Another question is the Milky Way unique? We're only looking at 13 simulated Milky Way analogs in FIRE. So in order to explore this, we can make comparisons between the different simulated galaxies. So we have 13 in FIRE, there's 30 in Auriga, but that's still a pretty small number. So another interesting thing we can do is use semi-analytic modeling, where we can rapidly generate large populations of Milky Way-like galaxies with their own stream populations. I'm currently working with a grad student at Princeton to use the code SatGen to generate satellite populations. We're implementing a stream modeling in there so that we can look at what happens to these stream populations as you change the host mass of the galaxy, properties of the disk, the accretion history of the galaxy. We know the LMC has a huge effect on streams and satellite populations. So we can explore all of this with semi-analytic modeling. Then finally, I think it's also interesting to look at how stream populations change as you change the dark matter model. So the FIRE simulations actually have Milky Way analogs that have been run with both self-interacting dark matter with elastic self-interactions and dissipative dark matter. So I'm also planning on looking into those simulations and seeing how the stream populations change as you allow dark matter self-interactions. And then all of this together will give us very strong predictions for the true population of streams that we expect to see in the Milky Way and the variation that's expected depending on properties of the Milky Way and between the different simulations and full understanding of the effects of resolution. And with all of this, we can make very strong predictions for what the stream population should look like in LSST. So it'll enable us to accurately and precisely constrain both dark matter and galaxy formation physics with these observations. Okay, so with that, I will leave up my summary and I would be happy to take any questions.
Really great talk. Lots of interesting, exciting results. So further questions going?
So V-band sky brightness of 34 magnitudes per square arc second is about 13 magnitudes fainter than the average V-band sky brightness. So that's about 150,000 times fainter. So how long do you have to expose with a 4-meter class telescope to reach that limit?
Yeah, sorry, it is a little bit confusing because it's a different definition of surface brightness. So these aren't streams that are detected in images. They're detected from resolved star catalogs. And so we calculate the surface brightness by taking stars that have been selected as member stars and then summing up the flux from those stars over the area. So it's a different number that can't be compared directly to the surface brightness limits. Yeah.
So just curiosity, so if you have a dwarf galaxy that is stripped and forms stellar streams, I guess in either simulations or observations, whichever comes to mind first,
what exactly happens to the dark matter halo? Does some of it go along with the stars, or is it just kind of get like warped, or what's there?
Yeah,
Great
so
if we figure that out in observations. It'd be great if we knew that in observations.
in simulations, we see that a large fraction of the dark matter has to be stripped before you start stripping any stars. So even around 90% of the dark matter mass gets stripped before you strip the first stars. So anything that's forming a stellar stream probably has a very small fraction of its dark matter remaining. But I do think this is another thing that would be really interesting to look into in these population of streams and cosmological simulations, is sort of explore how much of that dark matter mass gets stripped.
So there could be like long dark matter tails as well.
Yes, but it would be very low density. Yeah. Yeah.
You can decide. Yeah.
So I want to ask about your last point, this 10% of the mass goes into the tidal tails.
Mm-hmm.
So do you know which 10%? And the reason I ask is in our chemical abundance follow-up work on these kinds of things, right? So I took 3, we found out that they were all the stars were mildly R process enhanced. They all looked like roughly the same population. But then I think Teresa's paper, more recent paper, she finds 1 R process star and the rest of them look normal. So like, where are these stars that go into the tails coming from? And can we learn something about dynamics and be coupled together? You see what I'm trying to get at?
Yeah, so it's mostly in the outskirts of the galaxy. Do you have any suggestions for how that would be connected to the chemistry?
Well, I guess it would be interesting if all of the stars in a galaxy like Kentucky 3 are process enhanced, but it's interesting then if other galaxies only have a few R process enhanced stars. What is that? I don't know what that means in a phase mixing formation model kind of thing.
Yeah.
Like, how did that happen?
I don't know, but I do think it would be interesting.
So this might be a forward and
Yeah.
trying to figure that out. So that's
For the observed streams and satellites, are the mass estimates coming from orbital modeling, or is that coming from luminosity?
From metallicity. So then we use the stellar mass metallicity relation to convert to stellar mass.
You see an evolution of that based on the progenitor?
So we have explored the effect of using a redshift dependent mass metallicity relationship. And so it does, so right now we're using the Z0. So if we include this redshift dependence, would increase the masses of the stream slightly. And I think it's too much work to get back to that slide, but essentially when you look at comparing the mass functions of the detectable streams, it's actually slightly more consistent if you include some redshift evolution, but because we just don't have a great idea of where the streams lie in this space, since most measurements have been for intact satellites or more phase mix systems, we didn't include that here, but I think that would definitely be interesting, but it only sort of moves it within the scatter between simulations, if that makes sense. Yeah.
Too big to fail results, we showed how taking detectability into account resolves the discrepancy seen between simulations and solutions. Right? It's often said, validate that even with what we see in the streams, not the satellite, I guess the streams, essentially the entire Milky Way stuff, right? That's based on what we see. So if there's a lot we're not seeing, or that is obviously the things we're missing are lower surface frequency. Is that enough to say we actually have underestimated the halo? I guess the growth rate will be low because the halo mass must be.
Yeah, that's a good question. I'm not sure, but maybe because this is, so, you know, if FIRE is correct, it really is suggesting that the population of even the highest mass dwarf galaxy streams is much larger than we previously thought. Because, you know, before going into this, I kind of thought that something with a mass around Sagittarius we should have detected by now if it's still a stream. This is saying that there could be, you know, maybe 3 to 6 more within this mass range, very close to Sagittarius that we haven't detected. So that would make a big difference, I think.
I don't know if that would be significant for anything. I mean, the halo isn't all that massive.
Yeah, it's interesting.
Voice of God.
Oh, sorry, voice of God, go ahead.
I don't know how to take that, but I actually had a follow-up, I think, with or maybe a tag on to what Rob was saying. I mean, so it seems like, you know, the answer is there should be a lot more of these streams or the tidal features that are yet to be discovered. Is there another explanation? And like, where will we be after LSST? Like, if we don't see them, I guess, what would you think is the culprit then? Or do we just have to go deeper than LSST? I guess right now I'm left with the feeling that, okay, we're just missing a lot of streams, or, you know, they're low surface brightness, they've been tidally disrupted. How do we answer the question? I guess I'm just kind of curious what your thoughts are on that.
Yeah, I mean, so a lot of the work that I'm trying to do now is to make sure we really understand what it's going to mean if we do or do not see these streams in LSST. And that'll mean also sort of extending down to lower mass streams so that we have a better idea of what we expect the dwarf galaxy stream population to look like down to, you know, 10 to the 4th solar masses and stellar mass. But I think that if we really feel like that we confidently understand the effect of resolution, the effect of different simulation assumptions, the effect of, you know, the disk size of the Milky Way or the mass of the Milky Way, then it will be a very big question if we can't discover these streams that we're predicting in LSST. Yeah, so.
Okay. That's super interesting. Can I ask one more follow-up? I mean, and this is my ignorance. Is there any benefit to applying some of this modeling to things like M31? Is it just too far away to see these kinds of to get down to the masses we need and the surface brightnesses we need?
Yeah, I mean, I think that could definitely be interesting. The stream population is definitely less complete than what we have in the Milky Way, even in these high stellar mass ranges. And the detectability, the detection methods are slightly different. So I didn't include them in this analysis, but I do think it could be interesting to look at M31 and then also eventually with other surveys. So both Rubin and Roman will give us stream populations around external galaxies. I think will be really exciting.
Yeah, I agree. Just to have more data points could be useful. Anyway, it was really interesting. Thanks.
I've got a bunch more, but I'll save them for later. I'll actually just a final one here. Gaia data release 4 and data release 5 and beyond. How's that going to help?
So Gaia probably wouldn't be the most useful for detecting these streams that we're missing in the Milky Way, just because these are very low surface brightness and mostly very distant.
In terms of doing the follow-up though, like with kinematics.
Yeah, I mean, so even DR3 didn't have a huge effect on the way that I study stellar streams, at least, just because most of the streams are too distant for the new data that's included in DR3. So it probably won't have a very dramatic effect, but you know, it'll be helpful.
You're like right here, you're like too close to the magnitude limit, if not beyond it. Okay, so Nora will be around for the rest of today and the beginning of tomorrow. So there might be a spot or two left on our schedule. But if not, so let's thank her again. And